for this tangent line. Is it clear for everybody? If it's too small, I can try to write the font to be larger. Okay, so we can view it, or we can verify from the geometric view. Right? So how to do that? Let me just randomly draw a convex function. So suppose it's like this, right? It's a typical convex function, and we can pick up any point. This is some specific input x0. So of course, this x-axis is y-axis. Right? So let's try a variety of lambdas, right? So different lambda will correspond to different tangent lines. Right? So say I can just try a steep slope. Lambda is slope, right? Slope of the tangent line. So it's like this. Right? This is a tangent line. So we denote by lambda 1. Lambda 1 x minus g lambda 1. Right? So at x0, we can evaluate the value of the tangent line, which is here. Right? And of course, you can choose you can try another slope, say an active slope. Say I can draw a tangent line here. Lambda 2. Lambda 2 x minus g lambda 2. Right? You can randomly try a third line. Say let us try a tangent line which is nearly parallel to x. Something like that, right? So we got lambda 3. We got lambda 3x. Let me choose the it's the strongest line. Okay, lambda x 3x minus g lambda 3. Right? So for those three choices of lambda, we can evaluate its value at this particular point x0. So we get three function values on those which correspond to the three tangent lines, right? But the question is, which lambda can yield the largest value at x0, right? According to the definition here. So now you can tell me which lambda will end up with the largest function value at this specific input x0.
The one that intersects with the red line.
Yeah, right. So it's just a tangent line which passes x0 and fx0. So if you draw a perfect tangent line at x0, just draw a line which is right intersecting with fx at this particular point. Right? So at this point, if you evaluate the function value of this tangent line, at this point, you reach the maximum. Right? That's how we define fx in terms of maximum. Linking to the equation we previously mentioned, right? So we mentioned that this is a way to check whether a function is a convex or not. The right-hand side is essentially a tangent line, right? So we mentioned that for any convex function, if the function is differentiable, that basically means at any point you draw a tangent line, the line will stay below the whole function. So now we can say, okay, so for this particular function value at x0, say x0, right? You can draw arbitrary tangent line. You can draw arbitrary tangent line, but they will all below the whole function body, right? And only the function, the tangent line which passes exactly the point we're interested in, that is x0 here, you will reach the maximum because you touch the function body. So that's you can use this geometric view to understand why we define convex function fx in this way. And we can further verify the meaning of G lambda by observing this definition, this dual representation, right? We define the conjugate function of fx G lambda as the maximum of this lambda x minus fx with respect to x. So let's see what kind of geometry view we can get from this definition. So again, let us draw arbitrary convex function fx, right? And suppose this is an xy axis. So again, lambda x is a line, right, which passes origin. So you can arbitrarily draw a line like this, or like this, right? Different lambda. So you got like lambda 1, x, lambda 2x, right? So now here we assume lambda is fixed. So suppose we choose some particular lambda, and let me draw a good looking line. So let us fix lambda, and then the corresponding lambda x. It's too bad. Sorry for this. This function curve. Let me draw a particular line for a particular lambda. So this is lambda x, right? So let us take a look at the right-hand side. So the right-hand side is just difference between lambda x and fx. So this is a lambda x, and this is a fx. So how do we represent their difference? You just draw a bunch of vertical lines, right? And which connect the points on the two curves. Right? So let me represent this as green vertical lines. Those lines those green lines, the length of those green segments actually represent the difference, right? So of course, when we consider x in this part and in this part, so this x1 and x2, right? On the right hand side, this part, the value will be negative, right? Because fx is bigger than lambda x. Right? So when you subtract lambda x by fx, it will be negative. Similar things will happen for the right hand side for x2, right? So only between x1 and x2, you'll have the positive values. So among those positive difference, how do you find the largest difference? This is according to the definition on the right hand side. You want to find out the biggest difference between lambda x and fx. How do you find the biggest difference?
We find the biggest difference between the function and the lambda curve.
Yeah.
At some point.
Yeah. How do we find it? Just using simple geometry.
Just the derivative.
No, Joe.
Yeah, of course, it's related to the derivative, but how do you find it? If we are just like junior school student, how do we do that?
It's the point where the slopes are equal, correct? So it's, you find the derivative of each function and
yeah, exactly, right? So how do I find the longest?
You shift it down until you have only 1 point left.
Yeah, we just shift it, right? Shift it and just do parallel shifting. Right? Just move it. We know when we move it downward, it will keep crossing the function curves with 2 points, right? We move it until you just touch 1 point. You're tangent to that line. So when you move it until you only touch the function body once, right? At this particular point, you know this difference is the largest, right? So that will be the largest difference. That will be the G lambda, right? And again, because this is lambda x minus fx, so g lambda will be the negative intercept. And you can perform like similar analysis, like even you don't have a, say your lambda x is totally below this function. The similar kind of observation can be observed, can be concluded as well. So I'll leave it as an exercise for itself. So even like I don't have I don't cross this whole function model. If my lambda x is just here, I can still use kind of similar way to find the biggest difference, and you'll see it's still consistent with the right hand side. Any questions so far? And in the last lecture, some student asked me, like, so now that fx is convex, right? And Helen asks whether g lambda is convex or not. So the answer is yes. And moreover, the argument can be even stronger. No matter fx is convex or not, if you define g lambda in this way, g lambda will always be convex. So this is a very interesting conclusion, but the proof is pretty simple. I won't leave the video, but just give you a hint. So we know that g lambda is maximum of this lambda x minus fx, right? So we know for arbitrary lambda and x, we have g lambda is bigger or equal to lambda x minus fx. Right? Then you can try to incorporate the definition of the convex function. You can introduce arbitrary 2 points for lambda 1, lambda 2, and also a coefficient between 0 and 1. So just apply this inequality. You'll get like alpha times g lambda 1 plus 1 minus alpha plus g lambda 2 will be no less than alpha lambda 1 x plus 1 minus alpha lambda 2 x minus fx. So when we can merge these two terms. Is it clear, or I need to write it more clearly? So it looks like I need to write it more clearly. So the right hand side will be simply alpha lambda 1 plus 1 minus alpha lambda 2, because you merge terms, minus fx. You just apply the equality twice and add them together. You end up with this. And this one, that means because this inequality always holds for arbitrary x. So that means the right hand side is always here. It's bigger than or equal to maximum supreme of the right hand side. So this alpha lambda 1 plus 1 minus alpha lambda 2 times x plus fx. Right? Because that inequality always holds. We will take the maximum of the right hand side, the inequality still holds. So we will take maximum of this right hand side. What does it do? According to the definition here, right? So if you take the maximum of the right hand side with respect to x, you end up with g alpha lambda 1 plus 1 minus alpha lambda 2. So now you prove g lambda is convex. And we never make any assumption about fx. So it's an interesting practice. If you're interested, you can try to prove it by yourself. It's just apply the definition of convexity.
It's isn't it like for different lambda 1 and the lambda 2, the argmax x is also different?
Yeah, it doesn't matter because whatever x you choose, you always have a upper bound. Right? The left hand side is the upper bound for this, so it doesn't matter how do you choose x. You can choose arbitrary x and you add them together. It's fine. The key is that okay, when you add the two equations together, you can at the beginning because this holds for arbitrary x, right? You just fix x to get the first one and the second one, and then you add them together, you get the right hand side, right? And then you just take the supreme of the right hand side with respect to x. You end up with the definition here.
There is only one x.
Yeah. You can choose arbitrary x. You can choose arbitrary x. You get g lambda 1 is bigger than or equal to lambda 1 x1 minus fx1, right? You can choose you can use the same x1. So you get g lambda 2 is less than lambda 2 x1 minus fx1. Right? That means you fix x, you share x, because whatever x you choose, this inequality is always hold. And then you just vary x1. And then take maximum, it still hold. Does it make sense? Okay. Any question? So now let us switch to the matrix derivative.
Doesn't the same thing hold for fx also?
What?
For the fx in the previous slide. Doesn't the same thing hold for fx? If fx is of this form, fx has to be convex. Right?
If x is what?
Fx is of this form, max lambda x minus g lambda, then fx is convex.
If g lambda is convex,
Okay.
yeah, then fx is convex. Right? If you but if you define g lambda as in this way, no matter whether fx is convex or not, g lambda is always convex with respect to lambda.
Why can't we do the same thing for the upper equation, like just substituting x and lambda?
Yeah, you can do that. If g lambda is convex, then fx is convex for sure. And if you can define fx as this, no matter whether g lambda is convex or not, fx is always convex. But the problem is many non-convex functions cannot be represented in this way, right? So this is very commonly used in the variational inference. It actually forms the foundation of the variational inference. So I hope you can keep it in mind because later when we discuss about variational inference, we'll come back to this again. Any questions? Okay, so then let us go to the matrix derivatives. So because we were going to heavily use matrix derivatives, that is, if your objective function is scalar but your input is a vector or even matrix, how can we compute the gradient with respect to this the gradient for some particular vector for matrices? So I know it's kind of if you never used that before, it sounds tricky or sounds like non-trivial, but actually it's quite simple. And whenever you have to calculate the derivatives for matrices or vectors, just keep in mind, just come back to the original definition. That is what is differential. So what is differential? For the scalar version, differential means that, okay, if I do the expansion at any point x, right, as long as difference between your point you want to expand and between your current value and the point you want to expand is infinitesimal, you can approximate this function as a linear function. This comes from the basic calculus, basic definition of differential, right? The same thing applies to the matrix of vector derivatives. So if Now we have a vector function. See, y is an n by 1 vector, and the input x is also a vector, is n by 1 vector. So we can still represent the vector function y of x plus some dx. Dx is kind of a very tiny difference between x and y, but it's tiny vector. X, yx, the function value, which is vector at x, plus a matrix A, multiplying with this difference dx, and plus some all the terms. So usually these higher terms can be represented as all the terms of square norm of the dx, right? And so y is n by 1, and x is n by 1, so dx is n by 1. So the size of A here is an n by n matrix, right, to be consistent. So from the characters we know, A is also known as a Jacobian matrix, right? And we also define A as the derivative. That is, dy can be written as A multiplying with dx. Or you can equivalently represent as partial y or partial x equals to A. So now you know the rules, right? So y is n by 1, right? And x is n by 1. So their partial derivative is n by n. So the rows follow the length of the output, the function output, and columns follow the length of the input. So we choose the consistent. We choose the consistent definition of the Jacobian matrix. Yeah, I want to emphasize this point because probably you will see from other book they choose a different notation. You might see from other books they define that partial y or partial x is A transpose. Don't be confused at that. They're saying the same thing, but they use different custom. Why? That really is how you apply the chain rule. So suppose we want to use chain rule, same kind of thing. So I know, okay, I have a y function, which is n by 1, which is function of x, which is n by 1, right? And now suppose x another function. X is another function of theta, which is say q by 1. So if we use our notations here, how do we calculate the partial y or partial theta?
Can you just expand it to partial y over partial x and partial x over partial theta?
Yeah. So first we need to be clear what's the size of partial y and partial theta over partial theta, right? So y is n by 1, and theta is q by 1. So according to our definition, rows follow the output and the columns follow the length of the input, right? So it will be n by q. Right? So now we apply the chain rule from left hand side to right hand side. So we first do the partial derivative of y over x and multiply with partial derivative of x over theta. So let us check whether this matrix is consistent, right? So first, partial y over partial x, according to our custom, it should be n by n, right? And then partial x over partial theta, remember x is n by 1, theta is q by 1. So partial x over partial theta, which is n by q, right? So multiply the two matrices together, it ends up with n by q matrix. This is consistent, right? But if somebody chooses to define like partial y over partial x to be a transpose, which is n by n, right? So the row follows the input and the column follows the output. Right? What will happen?
It's still in shape.
It's just to do the chain rule from right hand side to left hand side. So just leave it as exercise for you. Then they will do things like this. They will first do the partial derivative of x over theta, and then partial derivative over y by x. So you see how they apply.
Can we just use initial notation so then we don't have to worry about this?
Yeah, that's the key point I want to emphasize here. So don't be confused. Choose a specific notation or custom and stick it to it. And for example, I never use this kind of definition because it feels kind of weird to me. But someone likes it. So you should choose whichever one you feel better, and stick to that. And when you find some other results, say from other customs, you get used to that. Don't be confused. That's my key point. Any question? Okay. So in general, how do we compute the matrix derivative or derivatives for vectors? Right? We're not required to derive all of those derivatives by ourselves. Instead, we have a bunch of commonly used results, well-known results. What you need to do is that to follow the basic rules to decompose your objective function, and then decompose them into basic components. Then you look up the existing results from the references I listed, plug them back into your decomposed form, you get full results. So here I just list a bunch of very commonly used results. Say the partial derivative. Let me use the marker. So the partial derivative of a constant matrix is just 0, right? Same as the scalar case. The partial derivative of a scalar multiplying with a variable matrix x is equal to alpha multiplying with partial derivative of the matrix, right? And also, partial derivative of the summation is equal to partial summation of the partial derivatives. And partial derivative of trace of a variable matrix x is equal to trace of partial derivative. And also, partial derivative of product. This is the same as the scalar case. And something I highly recommend you to keep it in mind, like partial derivative of inverse of a matrix, which is this form. Minus x inverse partial derivative x minus. Partial derivative of determinant of x is determinant of x trace x inverse partial derivative of x. Also partial derivative log determinant, because you will see that we have a lot of Gaussian distributions. If your covariance matrix or precision matrix contains parameters, you always need to compute the partial derivative of log determinant term. This is very commonly used. And what are the reference books which contain all the known results? The two references I listed before, right? The first one is coming from Minka. His X notes, all new matrix algebra useful for statistics, and another X reference, matrix cookbook, is very well known in the internet. Just download it, just look up, use it as dictionary. And another important tips for practice is that when you derive the partial derivatives, in addition to checking the results, a commonly used way to verify the results is to look at the size of your gradient. So the size of the gradient should be the same as of the size of inputs you want to take the gradient with. Okay. So now we have gone through the basic concepts in convex functions and matrix derivatives. I have released the homework 0 just to warm up and help you to get familiar with those matrix derivatives and definition of convex functions. And then in the following 3 weeks, we'll start with the foundation of the probabilistic learning and modeling. That involve a lot of concepts regarding probability, expectation, distributions, and commonly used multivariable distributions like multivariate Gaussian T distributions, derivative distribution, etc. Because as we mentioned before, those are like bricks. Right? You only have the bricks, you can build up your house. But I'm pretty much sure a lot of those concepts or definitions.
Could you come back to the previous slide and remind me the circle notation and the cross notation of the matrix?
The circle notation is the Hammond product. It's atomized product. And this cross notation is a Kronecker product. Yeah, Kronecker product. So just look up in the Wikipedia, you will find the definition of the Kronecker product. It's also heavily used. Any other questions regarding notations here?
So is that the outer product then?
No, it's not outer product. It's called Kronecker product. Well, if x and y both vectors, you can consider as a Kronecker. No, it's still not outer product because n by 1 Kronecker with m by n is n by 1. It's not n by n. This is not outer product. But I leave it as an exercise for you because I'm not gonna like teach this like for 2 or 3 lessons, for 3 classes, because it's quite easy to get used to calculate matrix derivatives following those references give you. Okay, we'll spend like 2 or 3 weeks reviewing those basic knowledge because I'm pretty much sure many of those concepts and the definitions you are familiar with or you haven't heard them. So my pace will be quite fast. But for those you might be very familiar with, I will stay slow and emphasize that. Does it make sense? Okay. So first, sample space, right? So what is sample space? Basically speaking, sample space is the set omega, which consists of all possible outcomes for some random experiments. So if we conduct some random experiments, we want to use probability theory, right? We want to introduce some probability structure to represent, to evaluate or to infer the chance of all kinds of events happening. Right? So before we describe this random experiments, we need to be clear what is our sample space. So here are a few examples. So if we toss a coin, our random experiments to toss a coin, then the sample space just consists of 2 elements, right? Head and tails. We'll have 2 outcomes. If we roll a die, suppose you are rolling a normal die, right? Normal dice, then you have 6 outcomes, 1, 2, 3, 2, until 6, right? And if you want to just measure the radioactive decay, then the sample space consists of the number of particles emitted per say minute. Then your sample space will consist of all the natural numbers, right? And also you can do like continuous experiments. Then your outcomes might be some continuous numerical values. Say if you measure the height of smooth trees, then your outcome will be positive, negative real values. And if you want to take a look at the image pixel values, there could be some bounded real values. So this is sample space. And then given the sample space, we can define events. So mathematically speaking, event is described by sets. So basically, an event is a subset that is contained in the sample space. Again, from the die rolling sample space, we can consider one particular event, that is, we roll an even number. So how can we represent this event? You have 6 points, you have 6 elements in the whole sample space, right? you just pick up those even numbers, which is 2, 4, 6, right? And similarly, you can construct another even. Say I roll the number is off. Then my samples, then my even is represented by another set with 3 elements, which is
135.
135, right? And in the spruce tree example, that is for continuous. So for continuous sample space, then your even is a subset, but the subset could be infinite as well. Say if my experiment is to measure the height of the spruce trees, and then I want to look at an even that the tree is taller than 50 feet, then my even can be represented by this range, right? Between 80 and infinity. So it contains an infinite number of the numbers, but it's still a set. So those are very basic, right? Everybody is comfortable with this, right? So, and then given a bunch of events, given several events, we can create or construct new events by using the set operations. So here are the 4 commonly used set operations: the union, the intersection, the complement, and the subtraction. Right? So correspondingly, for 2 events A and B, the union A and B represents the even A happens or B happens. Meaning that, okay, A happens or B happens or both happen. Okay? And the intersection of A and B represent another type of even, meaning that A and B both happen. And complement of A means a kind of negation operation, means that events other than A happen. I say one event is it's like it rains tomorrow, right? Then the negation of that will be it does not rain. It does not rain tomorrow, right? So, but it could be like snowing, it could be sunny, whatever. But it does not rain. Then it's negation of that event. A complement of that event. And subtraction. Subtract A by B just means that even A happens, but at the same time B does not happen. So we can say, using set operations, we can construct numerous new events based on existing events. Right? And then, given the sample space, right? And if you want to introduce, and also the random experiments, if you want to introduce some probabilistic structure to study our random experiments, we need to designate the set of all possible events. So remember, an event is represented by a set, right? The set of events is actually a set of sets. And the set of all possible events, our interest events, should satisfy some properties. Otherwise, it will end up with weird results. This is kind of counterintuitive. You cannot choose an arbitrary set of events to study and to do some probability assignments. If you do that, you could be end up with very weird results. Like for some particular event, you cannot have any probability assignments, or something like probability A happens plus probability A does not happen is not equal to 1. This is not allowed. So to avoid such kind of embarrassing situation, this is kind of embarrassing. We need the set of all possible events to satisfy the following properties. So first, the empty set must belong to F, the set of all possible events. And second, if you have like a bunch of events which belong to F, then their union must belong to F. And actually, this set of events can be uncountable, infinite number. But you need to ensure that the join of this infinite number of events must still belong to F. So it's closed on the joint, on the union of the events. And the third property is that if a particular event belongs to F, then the complement of even belongs to F as well. So it's closed under completion. So combining the first property and second property, we can say that the whole sample space, omega, must belong to F as well, right? So if we can choose such a set of events F that satisfies the three properties, we call this set of events as a sigma algebra. So sigma algebra is essentially a set of sets and which satisfy these three particular properties. First, empty set must belong to it, close under union operations, and close under completion operation. So only under sigma algebra we can define a consistent and well-behaved probability structure.
What was the 2 to the omega?
Oh, 2 to the omega is just the enumeration of all possible sets in omega. So basically, you can consider like I have 10 elements, right? So how can we pick up different sets from omega? You can pick up one element, you can pick 2 elements to form a set. You end up with 10 to the 10, 2 to the 10 number of sets. You combine them together, you give the complete sets of omega. And this one is for sure a sigma algebra. But in many cases, it's not necessary for you to use the full sets of the events. Any question?
So what happens if omega is not finite?
Doesn't matter. We're talking about theoretical properties. So probability measure. So given a sigma algebra, we can define a measure. So what is measure? Measure is essentially a function which maps from this sigma algebra to the non-negative numerical values. So basically, it maps each set to a non-negative number. That's it. So it also needs to, a valid measure must satisfy the two properties. First, the measure over the empty set must be 0. And second, for pairwise disjoint sets, so A1, A2, say to A infinity, they are pairwise disjoint. Any arbitrary 2 sets, their intersection is just empty. Then you need to ensure that the measure over the union of those disjoint sets must be the summation of the measure over each individual set. So to well understand it, you can consider this as a generalization or more abstractive definition over the commonly used concept like area. So if you compute the area for a rectangle, right? If it is not a rectangle, if its length and width is just 0, then the area is just 0, right? And if you partition this rectangle into several sub-rectangles, you need to ensure that the area over this whole rectangle is equal to the summation of areas over each individual sub-rectangles, right? So the measure is essentially a kind of generalization of the naive concepts like areas and volumes and such kind of things. So given the definition of measure, we can further define the definition of the probability measure. So what is probability measure? First is measure. Second, the measure over the entire sample space is 1. That is called probability measure. So now we can define a probability space. So what is probability space? It's actually a triple. Consists of 3 elements. First, omega is a sample space. Second, F is the sigma algebra, or you can also say it's an even set. And third, probability measure. That is, how do you assign a probability to any set in F, or any even in F. So some properties of probability measures. These are consistent with what you have learned about probabilities and statistics. So we just briefly mentioned. So the probability measure over completion of the set, or even A, is equal to 1 minus the probability measure over A. And probability measure over A union B is equal to probability measure over A, probability measure over B. So here, for briefly, I just call probability measure as probability of B, right? Minus probability of A intersecting B. Right? These are the results from our entry level statistics course, right? And conditional probability. Given probability space, the conditional probability for an even A given even B is defined as follows. So it is defined as the dividing the joint probability, that is probability of A intersecting B, right? Both A and B happen, by the probability of B. This is conditional probability. So here's example, right? So if we roll a fair die, right? So that means you get any point 1, 2, 3, 4, 5, 6 with equal chance, right? So we can define two events. First, the event A is represented by the set 2, meaning that okay, you only get point 2, right? And the second event B represent you get like even points, right? So it consists of 3 points, 2 or 6. And we know because it is a fair die, right? So the probability of A is 1 over 6. But the probability of A given B is what?
The intercept over the probability of B.
Yeah, according to the definition, right? Just apply the definition. So probability A intersecting with B, which is 2, right? This one, the intersection is just 2. So it's 1 over 6. And the probability of B is 1 over 2. So it turns out conditional probability is 1 over 3. And independence. Let A and B be two events in the sample space. We say A and B are independent given that the joint probability of A and B, that is the probability measure of A intersecting B, can be decompose the product of probability of A multiplying with probability of B. This definition of independence is just like very basic definition. Everybody knows, right? And we can define independence from the conditional probability as well. So how do we define it? Let us consider if A and B are independent, what is the conditional probability of A given B? Right? So according to the definition, it will be the joint probability of A and B divided by the probability of B. Right? So if A and B are independent, meaning that this joint probability is probability of A multiplying with probability B. And divided by the probability of B, just cancel it, get probability of A. So basically, you can say if the conditional probability of A given B is the same as the probability of A itself, then A and B are independent as well. So here are the general conclusions. So we say A and B are independent. Then the following conditions are totally equivalent. First, probability of A given B is equal to probability A. Probability of B given A is equal to probability of B, and also the joint probability of A and B is equal to the product of probability of A and probability of B. Right? They are the same thing. Random variables. So the random variable is a function defined on a probability space. So if we have a probability space omega I and P, right? Omega sample space, F is the sigma algebra, the even set, P is the probability measure. Then random variable F, the random variable is a function which maps from the sample space to a third set P. So you see, it's a mapping. Random variable is not a variable, it's not random, it's just a function or mapping. It maps the original sample space to a new set. And what set V do we usually choose? Numerical values or numbers. You can choose V to be like all real values, or you can choose to be integer values. So why do we define random variables? Because if you do not define random variables, you have to deal with those probability structures with sets, right? Sets and sets is really, really inconvenient. If we try to map the original outcomes of the random experiments, which are from sample space, right, to some numerical values, we know we're very familiar with numerical values. We have a lot of operations for numerical values, plus, minus, take exponential, take sine, cosine, whatever. Right? We have a lot of tools to deal with that. That's why we introduce random variables to convert everything into the numerical space and do the operations. But when we discuss random variables, we usually just assume, okay, it's some kind of numerical value, but in essence, it's not numerical value. It represents a kind of metric, a function. Just keep it in mind because this is just some conceptual steps. And when we do the calculation, when we do the modeling, we just ignore this part. And technically speaking, random variables are measurable functions. You are not necessary to know what are the measurable functions, just to ensure that your is reasonable. It's reasonable. At least you well, I think I don't want you to explain the detailed definition of the measurable functions. It's not necessary. So here give a nice example again, right? To give a definition. Let's give an example of the random variable. So this is our probability space, and we can define our random variable is a mapping from sample space to some integer values. Okay? And our random experiment is to roll the dice, right? And our random variable is defined as a summation of numbers of two dice. So essentially, we have two dice, and we roll it, and we get points, right? So for a particular outcome, which is a pair of the points, 1, 2. So the random variable is defined as summation of the points. So the value of the random variable will be 3. Okay. And the random variable for 4 is 8. And the random variable for 6, 5 is 11. Right? Any question? Okay. So even simple example. Say if your experiments are the outcomes of your experiments are also real values, you can choose the random variables to be an identity function. It means that, okay, I do not make any transformation. The outcome is directly the random variable value. Something like this. And given the random variable, we can use random variable to define events as well. How can we do that? We can use like the random variable being some particular value, or the random variable is less than or equal to some value, or the random variable falls in some range of numerical values to define events. So what are the corresponding events? For this particular event, that is the random variable function value is a particular value x. It corresponds to the event that, remember, event is a set, right? The set of outcomes. A set of outcomes for which each outcome has its corresponding random function value equals to this specific value x. So this sounds like tedious, but you should have this concept in mind. So when we say an event that the random variable is less than some particular value x, it means an event which is a set of outcomes where for each outcome the random variable, the corresponding random variable value is less than this specific x. And similarly, if you use a range that the random variable is between a and b, it corresponds to this event, right? So given the random variable, if your random variable is a real value function, that means it maps the outcomes to a real value. we can define the cumulative distribution function of x. The cumulative distribution function, also referred to as CDF, is defined as a specific probability over the event that the random variable is less than or equal to some specific input x. So this is consistent with the CDF definition we have learned before, right? It's just probability that the random variable big X is less than or equal to this small x. So what are the properties of the CDFs? So here are three important properties. Just refresh our mind. So first, f is monotonic increasing. So basically, when x1, we have x1, x2. If x1 is less than or equal to x2, then we have f(x1) is less than or equal to f(x2). It's reasonable because the probability that the event random variable less than or equals to x1 must be less than or equal to the probability that the random variable is less than or equal to x2, right? Because x1 is less than x2. So this event is a subset of this event. And also, the CDF is right continuous. So if you take the limit from the right hand side to x, it will approaches to fx itself, but it's not guaranteed to be left continuous. And also, when x takes the limit to the negative infinity, then the CDF is 0. And take the positive infinity, then the CDF turns to be 1. Right? So those are, I believe everyone knows that. And also, if your random variable is a discrete value, then we can define a probability mass function. So probability mass function is just the probability measure over this particular event. Remember, this represents a particular event, right? And then we can define CDF as summation. So the probability of the random variable x is less than or equal to some particular value, small x, is a summation of all the probability mass over the values which is less than or equal to x. Right? Probability density function. If your CDF is continuous, then we can take a derivative over the input x. You get the probability density function. And then we can rewrite the CDF as an integral over the PDF, the probability density function. Right? And the upper limit of the integral is the input x. So according to the definition of calculus, if you take a derivative over this integral function, it is equal to replace the you substitute for the input of the integrand you substitute this upper limit for this for the input of this integrand. Right? So this is basic calculus. And here is one simple example of uniform distribution. And you can have a uniform distribution of random variables. So you have a probability density between 0 and 1. The density is just 1, right? And for all the other places, density 0. And you can calculate the cumulative density function, which is something like this, right? Because before 0, you have no density accumulated, right? It's 0. And then from 0 to 1, when you're doing the integration, you get this linear function curve. And after 1, you have integrated out all the density. Non-zero density is you end up with 1. Just keep it 1. So you can see this is a right continuous. And this thing I need to emphasize. What will be the probability density when we transform random variable? Say, consider a differentiable function f, and we can transfer a random variable x to a random variable y such that y equals to fx. And now the question is that how do we compute the density for y? This is the result, but I think this is a bit complex. You can just memorize py is equal to the absolute value dx over dy times density over x. So because x can be represented as f inverse y, right? You just substitute x for this f inverse y, you get this result. Now, a more important generalization is that what if x and y are vectors? See, if y equals to fx, and y say is some m by 1 vector, and x is m by 1 vector, right? How do we compute density of y according to density of x?
It has to be.
So what does this term become? I just leave the conclusion for you. So if you're interested, you can take a look and search for the web. So now, to compute the density for y, we need to know the Jacobian partial x over partial y, which is the adjoint matrix, right? And then we need to compute the determinant of this Jacobian matrix, and then take the absolute value, multiply with the density of x, will not with density of the y. So this will be worth your notification because when you do some if you use like Markov chain Monte Carlo sampling, and there's kind of a type of method that's very efficient. Other kind of dynamic system which does not maintain the property. And that means when you do the transform, so every time when you sample new sample, you're given a current sample, you actually do a transformation. If the transformation does not ensure the Jacobian, the determinant of Jacobian matrix is 1, then you have to multiply this Jacobian matrix to correct it. Otherwise your sampling procedure is not correct. We'll say later if we go to the Hamiltonian sampling. Expectation. So expectation is just the integral of the random variable values and the density function, right? Of course, for discrete, the integral becomes the summation. So, but usually you do not need to differentiate the integral and summation because they are both summation. This is just the limit of the summation. Linearity of expectation. So this is a well-known property. So if you have like two random variables x and y and two coefficients a and b, the expectation of ax plus by is equal to a multiplying expectation x plus b multiplying expectation y. It's very useful property, and it extends to like an arbitrary number of the random variables. So the expectation of a linear combination of seven random variables is equal to a linear combination of the expectation of those random variables. If you want to compute expectation of function of random variable, remember a random variable is random variable, but the function of random variable is not a random variable. Right? So if you apply the function g over the random variable x, the gx is another random variable. So when you calculate this expectation, you do the integral again, right? So integrate gx with the density of x. So similarly for the discrete case, you do the summation. Variance. So the variance as random variable is defined as expectation of the square distance between your random variable and expectation of x. So basically it says on average how far away your random variable jumps from its expectation. So larger the variance, the more uncertainty your random variable. And also you can, it's trivial to show that the variable the variance is also can be written as the expectation of the square of the random variable subtracted by the square of the expectations. And if we take the square root over the expectation, you end up with this standard deviation. So standard deviation is to maintain the same unit as your random variable expectation. So here's the one very commonly used distribution, is normal distribution, right? So I think everybody knows that. Is there anyone who does not know the normal distribution? Okay, perfect. So a normal distribution is parameterized by two parameters. So one is the mean, the expectation. The other is the standard deviation. So this is the density function of the normal distribution. So I hope you're very, very familiar with that. So I hope you can memorize this forever and ever. So you can forget anything about probability and statistics, but just keep this in mind. Drawn distribution, right? So similar to our drawn distribution defined for events as our steps, right? We can define a drawn distribution over random variables. So given two random variables x and y, we can define its joint CDF, joint cumulative density function, as the probability that these two events both happen. Right? Random variable x less than or equal to the specified value, and random variable y less than or equal to the specified value. Right? This is actually the probability of the intersecting two events. Right? So this is the definition. And given the joint CDF, the cumulative density function, we can define the joint density. So the joint density is to take the partial derivative of the joint CDF over x over y. So take the partial derivatives twice. But someone may ask, okay, what if I exchange the order of the partial derivatives? Right? Take the partial derivative of this CDF over y first and then over x. The answer is the same. Just keep it in mind. And then you can rewrite the joint CDF as the double integral, right? Integral over the joint density over the two random variables. And the marginal distributions. Now that we have a joint density for two random variables, then we can compute the marginal density for each of the random variable. So it's simple. So the marginal density of x is the integral of the joint density over the other variable y. Right? Similarly, this is how we compute the marginal density for y, right? And for discrete case, we just do the summation. So here's some code example. Very simple example. Suppose we have two random variables, C and R. C means that you get code, or you do not get code. R means that you have running nodes or no running nodes, and both are binary random variables. So this table represents this probability mass functions, right? Probability that 0, 0 is 0.4, 4, 0, 1, 0.05, and blah, blah, blah. And based on that, we can compute the marginals, right? If you want to compute the marginal probabilities that running nodes is 0, we do not have running nodes, how do you compute it? You just do the summation, right? Just add all the elements in the first row. You get this marginal probability. If you compute the marginal probability that R being 1, you just add the elements in this row. It's very straightforward, right? So conditional densities. So what are conditional densities? So if x and y are random variables with drawn density Pxy, Pxy, then the conditional density of x given y equals to some specified y is this way. It's very similar to the form of the conditional probability. But here you should be careful. So this notation is defined as Px given the random variable y equals to this, according to the definition, C0 or 0 over or 0, right? C0 or 0 is just this element. And the marginal probability of R in 0 is this one. we can also define independent random variables. Independent random variables basically says, okay, the joint density can be written as a product of the marginal densities. Then it's independent random variables. And also, you can show that the conditional density is equal to the marginal density. Same thing. And also, you can show that when you do the integral on both sides, you get, okay, if two random variables are independent, then their joint CDF is equal to the product of their marginal CDFs respectively. Conditional expectation. Conditional expectation is just expectation over this conditional density. It's also an integral, but the density that is to be integrated. Expectation product two random variables. So how do we do that? You can treat the product of two random variables as a function of the two random variables, right? And then, according to the rule we just mentioned, how to compute expectation of a function of a variable. You just do the integral. Right? The integrand will be the function of the random variables multiplied with its density, right? So you end up with this. Covariance. So covariance to random variables is defined as this, right? So the expectation of x minus its expectation multiplied with y minus expectation. It can be also written as the expectation of xy minus the product of their expectations. So basically, covariance measures how much the variable x and y change together. So if x change and y also change substantially, then we say, okay, x and y has a large covariance, right? Otherwise, they have small covariance. And we can further introduce the correlation. The correlation is the covariance normalized by the standard deviations of the two random variables. So we can prove that the correlation is between -1 and +1. If the correlation is positive, it means that if x increases, then y decreases, right? Otherwise, if the correlation is positive, then that means x increases, y increases, or x decreases, y decreases, right? If the correlation is negative, then x increases, y decreases. It just change in the opposite way. And something you need to differentiate the concepts, right? So what's the difference between independence and correlation? So if two random variables are independent, then they must be uncorrelated. That means their covariance is 0. Their correlation is 0 as well. Right? But is it reversed? Is it reversely correct? The answer is no. If two random variables, their covariance is 0, or their correlation is 0, then that does not mean they're independent. You need stronger evidence. So basically, from independence, we can claim that the random variables are correlated, but reversely does not hold. If two random variables are uncorrelated, does not necessarily mean that the two random variables are independent. In other words, if two random variables are correlated, they must be dependent on each other. But if two random variables are dependent, does not mean they must be correlated. Okay, so our progress is amazing. So let us stop here. I'm glad that nobody feel like confused and uncomfortable with this. So yeah, so on Thursday we will start to review a set of commonly used probability distributions.